Okay, most of the calculations we've been doing in lab, we assume that we've got a coil. So we would regard this thing here as a coil of wire. But it's not a coil. A coil would all be pretty much in one circle. Okay? Pretty much close to a circle. The loops would all be, if the diameter is this, then the loops are within a confined plane. Okay? These are spread out. Loop, 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 loop. They're spread out a lot more than they would in what we would call a coil. We still get a decent approximation, and again, that's what we've been doing is approximations, thinking in terms of loops. Okay? A solenoid is characterized by a radius of a typical loop lengths over which the loops are spread. So, and the number of loops. So it, kind of looks like this, where you got a length L, a radius A, and you got N loops. Okay? I want to apply Ampere's law. So what I'm going to do is I'm just going to take some segment. I could take the whole solenoid, or I could just take a segment of it that has a number of loops. Okay, so I've got a path inside here. Okay? And if the loops are going in this direction, they're coming out of the path that I've defined. This is a path. I'm going to integrate around this path. Okay? So at this point, we penetrate the loop. At this point, we penetrate the loop. At this point, we penetrate the loop. Okay? I'm using the word loop for each loop of this coil, and I've got the word loop for the loop of integration, right? So I don't like using that word twice. The path of integration. This thing. Okay, in yellow. Okay, well, it has a length. I can't use L. I want to use L. But I've already replaced loop with path. So path starts with P. So I'm going to say length P. Okay? I get penetrated right by number of loops per unit length is N over L times P current loops. If the current is I, then how much current penetrates these loops? you have this many loops penetrating the path, penetrating the region bounded by the path. I think I said the wrong word there and you're looking confused. Okay. How many? I say the path of integration has length p, so it's interior. In other words, the region bounded by the path, okay? And that would be this rectangular region here. Okay, well, how many loops are there? N over P, N over L, which is the number of loops per unit length, right? Times the length. Okay? P is the length, right?
P is the length of the path.
P is the length of the
L is
path.
the length of the whole thing.
Bad word. I mean, not a bad word, but I could make it one. But the, yeah, bad notation. Okay. Okay. Probably shouldn't have chosen P, but I did.
That's all right.
Okay? And this has nothing to do with the integration constant of a non-homogeneous linear differential equation, right? The integral of little p.
Right.
Okay. We're not doing that.
We're not doing
Okay,
P.
we'll do that tomorrow.
I agree.
We did that yesterday. We've done that a lot.
Right.
Okay. Let's not digress. Understand, if we do the number per unit length times the length of the path,
Right.
we get the number of loops. So if the current is I, then the interior of the path is penetrated by current N over L times P times I, right? So now what does Ampere's law tell us about the integral of the magnetic field around the path?